How small errors reshape the cosmos. At first, the difference was laughably small. Too small to matter. Too small to notice. A rounding error. A tiny imbalance. A value slightly off from perfection. In everyday life, it would have been ignored. But in the early universe, that microscopic error changed everything. These were not dramatic deviations, but subtle variations. Density differences of merely 1 part in 100,000. Yet from these imperceptible irregularities emerged every structure we observe today, demonstrating how profoundly sensitive cosmic evolution can be to initial conditions. To understand why this matters today, we need to go back to a time when the universe was almost perfectly uniform. Matter was spread evenly. Energy was smooth. There were no stars, no galaxies, no structure of any kind. Just an expanding field of near-perfect balance. In those earliest moments after the Big Bang, the cosmos exhibited remarkable homogeneity. Looking in any direction revealed essentially identical conditions. The same density, the same temperature, the same composition. This uniformity extended across vast distances, creating a universe that appeared featureless and monotonous, lacking any hint of the complex structures that would eventually emerge. In that state, perfection was dangerous. A perfectly uniform universe will remain empty forever. Nothing would clump. Nothing would collapse. Nothing would ever happen. Structure required mistakes. If absolute uniformity had persisted, gravitational forces would pull equally in all directions, creating no net attraction to draw matter together. The universe would expand indefinitely as a thin, cooling gas, forever spreading apart without any regions differentiating themselves. No galaxies would form, no stars would ignite, no planets would coalesce. Perfect symmetry meant perfect sterility, and those mistakes were tiny. Differences in density so small they were nearly indistinguishable from noise. Slightly more matter here, slightly less there. Errors measured in fractions of percent. These variations originated as quantum fluctuations, microscopic irregularities arising from inherent uncertainty at the smallest scales. During the universe's explosive inflationary expansion, these quantum jitters were stretched to cosmic proportions, embedding subtle ripples into the fabric of space-time itself. The imprints were barely above the threshold of detection, yet they carried profound consequences for everything that followed. At first, these imperfections did nothing. Expansion washed them out. Gravity was weak. The universe looked the same everywhere. But time was patient, and gravity remembers. The early universe expanded so rapidly that density differences seemed utterly irrelevant. Space stretched faster than gravity could respond, diluting any tendency for matter to aggregate. For tens of thousands of years, the cosmos remained a nearly uniform plasma where radiation pressure prevented gravitational collapse. The errors persisted but lay dormant, waiting for conditions to shift in their favor. As the universe grew older, those tiny differences began to matter. Regions with slightly more matter pulled in a bit more. That extra pull attracted even more. A feedback loop began. What started as a negligible error slowly became dominance. Once the universe cooled sufficiently that radiation no longer dominated, matter began responding to gravity's patient accumulation. Regions that were even marginally overdense started attracting surrounding material. This increased their mass, strengthening their gravitational pull, which drew in yet more matter. The process was self-reinforcing. Small advantages compounded over time into decisive differences. This was the moment the cosmos took shape, not because of grand design, but because of accumulated imperfection. Small errors did not cancel out. They amplified. And once that amplification began, the universe could no longer remain smooth. The transition from near uniformity to structure was gradual but inexorable. Over millions of years, the tiny ripples grew into density contrasts large enough to overcome expansion's smoothing effect. Matter collapsed into the first structures, diffuse clouds that would eventually become galaxies, forming filaments and clusters that trace the patterns of those primordial fluctuations. Galaxies, stars, and eventually planets trace their origins to those initial mistakes. If the early universe had been more precise, nothing familiar would exist. No structure, no history, no observers to notice it. Every astronomical object we see today, from asteroids to galaxy superclusters, owes its existence to those infinitesimal early irregularities. Without them, the universe would have remained a featureless expanse of thinning gas, expanding forever into cold emptiness. The very possibility of complexity, and therefore of life, required that the early universe not be perfectly uniform. How small errors reshape the cosmos is not a story about failure. It is a story about sensitivity. When systems are vast enough, even the smallest deviations can decide everything. The universe demonstrates how initial conditions, however tiny, determine long-term outcomes in systems where processes amplify differences rather than erasing them. At first, these early imperfections seemed insignificant compared to the scale of the universe. Expansion was overwhelming. Space stretched faster than gravity could react. Any small imbalance should have been erased, smoothed away into nothing. The initial expansion rate was so enormous that cosmologists might have expected the universe to approach perfect uniformity as it grew, with random variations averaging out across vast volumes. Yet this expectation proved incorrect. But gravity does not forget. It accumulates. Unlike forces that can be shielded or canceled, gravity is purely attractive and always cumulative. Every bit of mass contributes to the gravitational field, and denser regions exert stronger pull on their surroundings. This patient accumulation meant that even as the universe expanded and matter thinned, the relative density differences, the ratios between overdense and underdense regions, persisted. Gravity embedded memory into the spatial distribution of matter. As space expanded, matter thinned, but the relative differences remained. Where density was slightly higher, gravity pulled a little harder. Where it was lower, matter drifted away. The universe began to separate into winners and losers, not by design, but by arithmetic. The mathematics of gravitational attraction and cosmological expansion created a competitive dynamic. Regions that started even marginally ahead gained increasing advantage. Those that started behind fell further behind. The cosmos developed structure through differential growth, where initial tiny variations determined ultimate fate. This created a quiet conflict between two forces. Expansion tried to spread everything evenly. Gravity tried to amplify differences. For a long time, expansion dominated. The universe stayed smooth, almost boring. But gravity only needed patience. The competition between expansion and collapse defined cosmic evolution. Early on, expansion won decisively, stretching space so rapidly that gravity barely had time to act. But as the expansion rate decreased over billions of years, gravity's persistent accumulation began to prevail. The balance shifted gradually but decisively toward structure formation. As time passed, the pull of those tiny errors grew stronger. Regions that were barely denser began to slow their expansion. Matter lingered, then gathered, then collapsed. What began as noise turned into structure. The overdense regions reached critical points where their own gravity could overcome general expansion. They stopped growing with the universe and began contracting instead. Matter flowed inward, increasing density further, accelerating collapse. These collapsing regions became sites where the first stars ignited and the first galaxies formed. This process was brutally efficient. Once imbalance crossed the threshold, growth accelerated. Dense regions became denser. Empty regions emptied further. The universe fractured into clusters and voids, guided entirely by those initial imperfections. The cosmic web that astronomers observe today, with its filament of galaxies surrounding vast empty voids, descends directly from those tiny early fluctuations. The large-scale structure of the universe maps precisely onto the statistical properties of quantum fluctuations from the first moments after the Big Bang. What makes this unsettling is how fragile the outcome was. Change the early errors slightly, and the universe looks completely different. Too smooth and nothing forms. Too uneven and everything collapses too quickly. The cosmos balanced on a razor's edge. If initial fluctuations had been slightly smaller in amplitude, gravity would never have gained sufficient advantage over expansion, and structure formation would have been prevented. If they had been slightly larger, matter would have collapsed into black holes too quickly, preventing stable structures like galaxies. The universe inhabited a narrow window where structure could form at the right pace and scale. By this point, it was clear that the universe was not shaped by averages. It was shaped by deviations, by tiny numerical differences that history magnified into everything we see. The mean conditions of the early universe told almost nothing about its future. What mattered were departures from that mean, statistical fluctuations that broke the monotony. The universe we inhabit emerged not from typical conditions, but from rare fluctuations that happened to have the right amplitude and scale. The cosmos was not built from perfection. It was built from error. This realization inverts intuitions about how order emerges. Structure arose not despite imperfection, but because of it. The mistakes in initial conditions were not flaws to be corrected, but essential ingredients for everything that followed. The conflict deepened when scientists realized these tiny errors were not accidents of measurement. They were embedded in the universe from the beginning. Quantum fluctuations, amplified by rapid expansion, were frozen into space itself. Randomness became architecture. The irregularities were not imposed from outside. They were intrinsic features arising from quantum uncertainty during inflation. These quantum jitters were stretched by exponential expansion until they became classical density perturbations spanning millions of light years. The randomness fundamental to quantum mechanics became encoded in cosmic structure itself. This buildup revealed a disturbing sensitivity. The universe was not robust to detail. It was exquisitely fragile. Large-scale order depended on microscopic irregularities, surviving long enough to grow. Reality hinged on noise. The connection between quantum indeterminacy at the smallest scales and galactic structure at the largest scales demonstrated how deeply interconnected different levels of physical reality are. Tiny causes produce enormous effects through amplification over cosmic time. If those fluctuations had been slightly weaker, gravity would never have gained traction. If they had been slightly stronger, structure would collapse into chaos. The universe did not settle into form despite uncertainty. It relied on it. The quantum uncertainty that seemed like a laboratory curiosity turned out to be the seed of all cosmic structure. Randomness was not an obstacle to order, but its source. Emotionally, this was unsettling. It suggested that existence was balanced on coincidence, that everything familiar emerged not from inevitability, but from narrow tolerances. The cosmos was less like a machine and more like attuned instability. The sense that the universe followed necessary laws gave way to recognition that outcomes depended on contingent initial conditions that could easily have been different. Our existence appears to depend on parameters falling within specific ranges that seem neither obviously necessary nor easily explained. As models improved, this picture only sharpened. The distribution of galaxies matched the statistical fingerprint of those early fluctuations. The errors were no longer abstract. They were visible, stretched across billions of light years. Observations of the cosmic microwave background revealed temperature variations matching predictions from inflationary quantum fluctuations. Galaxy surveys showed clustering patterns corresponding to the expected growth of primordial perturbations. Theory and observation aligned perfectly, confirming that today's structures descended from those ancient errors. By this point, the role of imperfection was undeniable. Precision did not create the universe we see. Deviation did. Structure was born from imbalance, guided by gravity and locked in by expansion. The cosmos we inhabit exists because the early universe was not quite perfect, not quite uniform, not quite smooth. The universe did not overcome its small errors. It was shaped by them. The climax of this story is a reversal that still feels counterintuitive. The universe did not emerge in spite of small errors. It emerged because of them. This inversion transforms how we understand cosmic evolution and the nature of order itself. Once this is understood, perfection stops looking desirable. A flawless universe will be empty, smooth, and silent. No galaxies, no stars, no chemistry, no observers. Structure requires imbalance. History requires deviation. Perfect symmetry, while aesthetically appealing, is sterile. It produces stasis, not development. The richness of the observable universe depends fundamentally on departures from perfection. Those tiny early errors were not noise to be corrected. They were seeds. Gravity amplified them. Expansion preserved them. Time turned them into everything familiar. The largest structures in existence trace back to differences smaller than 1 part in 100,000. This represents dramatic amplification. Microscopic causes producing macroscopic effects through gravitational instability compounding over billions of years. This realization reshaped cosmology. It showed that averages do not tell the full story. The universe is not governed by what is typical, but by what deviates. Rare fluctuations decide outcomes. Small differences determine fate. Understanding cosmic evolution requires tracking not just mean values, but statistical distributions. Understanding how rare events and outliers drive the most significant developments. More deeply, it reshaped perspective. Stability is not the absence of error. It is a controlled growth of it. Complexity does not emerge from perfection, but from imbalance held just long enough to matter. This principle characterizes how order arises in complex systems generally. Growth and development require departures from equilibrium that are neither too large nor too small. Today, this principle echoes far beyond cosmology. In climate, in biology, in systems of every kind, tiny variations, amplified over time, reshape entire worlds. Sensitivity is not a weakness of reality. It is its creative engine. Biological evolution depends on genetic variations that are initially rare. Climate dynamics amplifies small forcing changes into dramatic shifts. Economic systems transform minor innovations into transformative technologies. Everywhere, small causes produce large effects through amplification and feedback. How small errors reshape the cosmos is not a story about fragility. It is a story about leverage. When systems are vast, the smallest differences can carry the greatest power. The universe demonstrates that in systems with positive feedback, initial conditions matter profoundly. Tiny perturbations determine ultimate outcomes, making history sensitive to details that initially appear negligible. Sometimes the smallest shift in perspective becomes the beginning of a new future. How